Hello, everyone.
Good morning.
Good morning.
Sending out an email real quick. I'll be right back while I'm waiting for you guys to log in.
Good morning.
Good morning. All right, now I'm ready to roll. Anybody have any questions before we get started? Nada, zilch, none, not a bit.
Homework question.
Okay, well, I've got some plans.
Someone has a question.
Oh, go for it. Who's that?
I had a homework question.
Oh, go for it, Lauren. If it's not too long, we can do it. Do you need to share the screen?
Yeah.
Okay,
I'll pull it up.
let me work on that. We still got people coming in, so go for it. You should be able to share now.
Okay. I had to pull it up.
I did post some more videos on my YouTube channel, and I also shared some more to the Canvas page. So y'all should look and see some of the examples we've worked, and we're going to work at several examples today. A couple of them are ones that I suggested you do on your own, so you're going to actually see the right answer now and make sure you get it right. Okay, a small block of mass m is given an initial speed v0 up a ramp inclined at an angle theta. To the horizontal, it travels a distance d up the ramp and comes to rest. What can you say about the coefficient, the value of the coefficient of static friction? Okay. Mu s is greater than or equal to mu k. I would think that's correct. But it told you that was wrong?
Yes.
So what's this question say? Let me move my box here. It's all up in my way. So it says, what can you say about the value of the coefficient of static friction? Express your answer in terms of the variable m, v0, theta, d, mu k at appropriate constants. So I guess it's wanting you to actually work out what the static friction is because, okay, I see, yeah, because it comes to an actual rest. So basically it goes up, the kinetic energy, the kinetic friction basically steals all the kinetic energy that it has. And then when it comes to a stop, the static friction is actually large enough to hold it in place. So what that means is the mu static friction is greater than or equal to mg sine theta. Let me write it on a piece of paper here. So let me turn my document cam on. So what we have is an inclined plane, angle theta, and it was like here, moving up with a velocity v0, and then it came to rest, let's say, up here. What we know is it has a weight mg acting on it, and then it also, once it comes to a rest, it must have a friction force F static, which is equal to, or is greater than or equal to, or actually I should say less than or equal to mu static times F normal. But we also have a normal force acting on it, F normal. So if I make my coordinate system X and Y like this, then I can break down the components of the weight like this. I will say this component of weight points in the negative X direct, or the negative Y direction. This component points in the negative X direction. This angle is going to be theta. So this would be mg cosine theta, and this would be mg, this is just plain mg, but this will be mg sine theta. So what we can conclude is, one, that the normal force, F normal, is equal to, this is from the summation of forces in the y direction equals mass times acceleration in the y direction, and that acceleration is 0. Because of that, I'd see Fn minus mg cosine theta is equal to 0. So I can say this is equal to mg cosine theta. And then the summation of forces in the x direction equals mass times acceleration in the x direction. It's sitting still, so that's 0 as well. So in this case, I've got mu static. I'm going to go ahead and put in Fn here because I know mu static times Fn is the biggest scenario we have. So mu static Fn could be representing this static force. It might be less than that. But in fact, that minus mg sine theta has got to be, it's got to be less than or equal to 0. Let me see, make sure that's, no, it's got to be greater than or equal to 0. Sorry about that. So if you pull the mg on the other side, you get mu s Fn is greater than or equal to mg sine theta. So mu s is greater than or equal to mg sine theta. And then, of course, normal force is mg cosine theta. So I would say it's greater than tangent theta, because sine over cosine is just tangent. You see how I did that?
Can you bring it in a little closer?
Yeah, it's awful green, ain't it? So the mg's cancel out. You just get sine over cosine, which is tangent theta. Any questions on that?
Can you try that up one more time?
Did you try that answer, Lauren?
Can you put it up one more time?
Okay. Just type in tangent theta for the answer.
Get theta?
Sine over cosine is tangent, so just type in tangent theta. Tan parenthesis theta.
About the mg.
No, the mg's cancel out. Okay. All right. I guess I'll save the rest of the homework related questions for the end. You are welcome to stay as late as you want, of course, or almost as late as you want. I do have another class starting after this, but there's a little break in between. So what I wanted to work on today was some gravity problems. We did learn, for instance, that Newton's law of gravity says that there's a force of attraction, and it's always attraction, by the way, between any two objects that have mass. And that force of attraction is the gravitational constant of the universe times mass 1 times mass 2 over the distance between their centers of mass, r squared. Okay. And it will act along that line, the force will, along that line, connecting the center of mass of M1 and the center of mass of M2. We know that G is about 6.67, times 10 to the negative 11th Newton meters squared per kilogram squared. I also know that the radius of the Earth is about 6.38? Yeah, 6.38 times 10 to the 24th, or excuse me, 10 to the 6th meters. That's 6,300,000. Man, I can't write without messing something up. 6,380,000 meters. Just because I messed that 6 up, I wanted to make sure y'all can make out what that is. Okay. We also know that the radius of the orbit of Earth is 1.496 times 10 to the 11th meters. We also know that the mass of the sun, let's do mass of the Earth first, because we're going to use that in a second. The mass of the Earth is in fact 5.98 times 10 to the 24th kilograms. And the mass of the sun is 1.99 times 10 to the 30th kilograms. And the orbit for the sun, for the moon, I should say mass of moon. Mass of the moon first is 7.35 times 10 to the 22 kilograms. And finally, the radius of the orbit for the moon is 384 times 10 to the 6th meters. Okay, that's a bunch of data that we'll be using in the problems. So I wanted to go ahead and give you all that up front. So I know G is 6.67 times 10 to the negative 11th. These numbers you can actually find in the inside cover of your text. If we were on a test, you of course would be able to just look that up, or even it would be given to you, would be acceptable as well. Okay, the circle with a cross in it is the symbol that we understand as being the Earth. The circle with a dot in the middle is the symbol we use for the actual sun, for obvious reasons. And let me share my screen with you so you can see the problems that I'm working first. So I've got that zoomed in at about 140%. That's pretty good. There you go. Make it a little higher. So you see, I'm asking compute the gravitational acceleration at this lowest point on Earth. And I said, where is that and what is the percent difference? Well, the lowest point on Earth is actually in the southern end of the Marianas Trench. And the Mariana Trench, southern end is actually called Challenger Deep, named after the Challenger craft. And it's actually 36,200 feet deep. So deepest is Challenger Deep. And that is, as I said, 36,200 feet. But we don't want that in feet. And I've already converted that to 11,034 meters. Okay. Notice the next question is compute the gravitational acceleration at the highest point on Earth. Where is that and what is the percent difference? So the highest is the peak of Mount Everest. Which is on the border with China and I want to say part of India. But anyways, I'll let y'all look that up yourself. Now, the elevation of that is 29,029 feet, which again, we don't really want in feet. So I took the liberty of converting it to meters as 8,848 meters. Okay. So we can go ahead and do number 1 and 2 of this question right now. I'm going to show you that stuff I just wrote down, though. Okay.
Okay. Yeah. Thank you.
I wondered if that was what you're asking. Gotcha. So what I wrote down was the deepest spot is Challenger Deep, and it's 36,200 feet deep, which is 11,034 meters. And the highest point is the peak of Mount Everest, which is 29,029 feet, which is kind of a cool number, easy to remember. And it's 8,848 meters. So gravitational acceleration we got again from saying your weight, which is mg, is equal to the gravitational force, which is your mass times the mass of the Earth over r of the Earth squared, because we're assuming that you're at sea level basically. When you do that, you can see that the m's cancel out. So you see g, gravitational acceleration, little g, is just big G times the mass of the sun times your distance away from the center of the Earth. Okay. So I'll say G for Challenger Deep so GCD, is equal to 6.67 times 10 to the negative 11. I want to leave the units off. We know how they all work out now. The mass of the Earth, of course, is 5.98 times 10 to the 24th kilograms. Remember, this was Newton meter squared per kilogram squared. So we're basically going to get a Newton meter per Newton meter squared per kilogram when these two cancel out. And then down here, the 2 meter squareds will cancel out. So we get a Newton per kilogram. But a Newton per kilogram, since a Newton is kilogram meter per second squared, a Newton per kilogram is just a meter per second squared. So the units all work out. Now, what I'm going to say for my radius, that's the sort of weird part. I'm going to say it's the radius of the Earth, which is 6.38 times 10 to the 9th, or excuse me, 10 to the 6th, minus, in this case, 11,034 meters, and I'm going to square that. Okay. Well, when you put that in your calculator, and I went ahead and did this to make sure I wouldn't make any careless mistakes during class, I ended up getting 9.833 meters per second. So y'all can double check that to make sure. So 9.833 meters per second. And I asked what the percent difference would be. Well, the percent difference for that would be equal to, I'm going to do big one minus small one, 9.83. That's the proper number, sig figs, minus 9.80 divided by 9.80. And then I multiply by 100 to convert it to a percent. And when I do that, I get basically 0.03 divided by 9.8. And that gives me 0.3, or excuse me, 0.31%. It's actually 0.306, but that's close enough. Okay, so it's not a huge difference in being at the deepest place on the Earth. But yeah, the gravitational acceleration is slightly higher, which means your weight is slightly higher as well. Now, the other question was the same thing, except this time they were asking for the gravitational acceleration at the peak of Mount Everest. So I'm going to call that G sub ME. Does anybody have a question about that?
What was that percent difference?
0.031 or 0. It actually came out to 0.306 was what I got.
Okay, and can you write down how the units cancel out?
Oh yeah, no problem. So in this case, it was Newton meter squared per kilogram squared for the G. And then I multiplied it by 1 kilogram for the mass of the Earth. And then I divided it by meters squared, like that. So you see the meter squared cancels out with both of the meters. And, oh, this was kilograms squared, by the way. I left off an exponent. So this actual kilogram just cancels out one of those kilograms. So I'm left with Newton per kilogram. But the Newton we know from F equals ma is kilograms times meters per second squared, right? So kilogram, well, you can't read that, can you? The Newton, 1 Newton is 1 kilogram meter per second squared. So if you divide the kilogram out of the Newton, it just cancels that out. And so you're just left with meters per second squared. Does that make sense?
Is it planning to make your focus the camera a little bit more?
So you should always remember what the unit of a Newton is. A Newton is a kilogram meter per second squared, and that comes from F equals ma. Because the meter, the mass is kilograms, and the acceleration is meters per second. And then when you do all this rigmarole, you get newtons per kilogram. And the definition of a Newton is a kilogram meter per second squared. So if I divide out that kilogram, I have no kilograms, I just have meters per second squared. Does that help?
Yes, thank you.
No problem. Those are exactly the kind of questions you should be asking. I want to make sure everybody always knows how the units work out. Every time you get a new equation, check the units, make sure you can make them make sense, or they're probably going to be a problem. And doing so will also help you remember the formula. So if you have a problem with trying to memorize things, doing that first helps. And then after you solve enough problems, you'll remember it. Okay. So the gravitational acceleration at Mount Everest, at the peak of Mount Everest, is going to be 6.67 times 10 to the negative 11th. I'll write the units this time. Newton meters squared per kilogram squared. That's going to be multiplied by the mass of the Earth, which is 5.98 times 10 to the 24th kilograms. And that's going to be divided by the square of the distance between them. Well, now the distance between them is going to be 6,380,000 meters plus the height of Mount Everest, which is 8,848 meters. So you see that 8 comes up right on here. So it's going to be, instead of 6.38 times 10 to the 6, it'll be 6.388 times 10 to the 6. And that's meters, and that's squared. So because of that, this meter cancels out all those meters. This kilogram cancels out that kilogram, and I get a Newton per kilogram again, which, as we said, was just a meter per second squared. In this case, the answer turned out to be 9.772 meters per second. So we call that 9.77. Notice it again is different by 0.03. The other one was 9.83. This one's 9.77. So it's really a difference of 0.03. And therefore, the percent difference would be 9.80 minus 9.77 divided by 9.80 times 100 to make it a percent. And again, I'll get 0.30, I think it was 61 or 306 again percent. So if you don't care as much as 0.5%, it's not going to bother you to ignore elevation or even the fact that you're under the sea when you use the acceleration of gravity being 9.8 meters per second per second. If you want it to get better than 0.5%, then you're probably going to do that. So any questions on that one? So this one was number 1. This one was number 2. All right. So let's look at sharing the screen again. I'm going to show you the next problem I've got made up for you. So we did 1 and 2. What I want to know is what's the average force of gravity of the sun on the Earth, and then what is the average force of the moon on the Earth. So both of them are pulling on the Earth with a force of gravity. And of course, the sun is way, way more massive than the moon. The moon's like 10 to the 22 kilograms, and the mass of the sun is like 10 to the 30th. But the distance between the sun and the Earth is way bigger. It's like 10 to the 11th, whereas the distance between the moon and the Earth is more like 10 to the 8th. So we're going to actually compare those now. So what I'm going to do is calculate first the mass, the force of gravity. So I'll say F, and I'll say that's between the moon and the sun and the Earth. So now I'll turn back here. I've already got the data on the sheet that we'll need. So I'm going to stop sharing my screen. And we'll say the force of gravitational attraction between the sun and the Earth is 6.67 times 10 to the negative 11th.
Can you move your paper up? It's a bit
Oh,
low.
thank you. I thought I'd done it far enough, but I didn't. 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared times the mass of the sun, which is 1.99 times 10 to the 30th kilogram times the mass of the Earth. And the mass of the Earth, of course, is 5.98 times 10 to the 24th kilograms. And the distance between them is 1.496 times 10 to the 11th meters, and that'll be squared. If I do all these calculations, notice the kilograms will cancel out with the kilograms. The meters will cancel out with all the meters, and I'm just left with newtons. When I plug this into my calculator, I get 35.47 times 10 to the 21st newtons. That's one extra sig fig, by the way.
Can you bring it up a little closer? It's very blurry.
Yes.
So this is the gravitational force between the sun and the earth?
Mm-hmm. This is the one that actually provides the centripetal acceleration necessary for the Earth to stay in nearly circular but really elliptical orbit. Okay. Now we're going to do the same thing, only this time we're going to do it for the moon. So the force of the moon on the Earth is going to be 6.67 times 10 to the negative 11th. We saw how the units worked out last time, so I'll leave that off. Now I need the mass of the moon, which is 7.35 times 10 to the 22 kilograms. And the mass of the Earth, which is 5.98 times 10 to the 24. And of course, I said I'm going to leave the units off, and then I started writing units. Now, the distance between them is the orbit of the moon's radius, and that's 3.84 times 10 to the 8th meters. So I'd actually given it to you as 384 times 10 to the 6th, but I just went ahead and moved the decimal place 2 places to the left, so it'd actually be in the pure scientific notation as opposed to engineering notation. When I do this calculation, I end up getting, and y'all should probably verify this, but it's 198.8, carrying one extra sig fig, in other words, times 10 to the 18th newtons. So it's like a factor of, well, this would be 10 to the 20th, and that would be 10 to the 22, technically. So 2 times 10 to the 20th and 4 times 10 to the 22. They're pretty close, but you can see it's basically a factor of 100. Okay. Any questions on that?
That number's in the denominator. That's just the distance between the moon and the Earth.
Yeah, from the center of the Earth to the center of the moon.
Hey, Mr. Younger, on
Yes.
the first one that you did, or the second, I don't know, FSC, that one.
Uh-huh.
Yeah. What are the units? It was really blurry, so I couldn't read them.
Okay. Let me pull it up closer to you. It's the G is Newton meters squared per kilogram squared. And then, of course, when you multiply it by kilogram and then kilogram again, those cancel out. And then you divide it by the distance in meters, which is squared. So that's going to cancel out the meters squared in the top. So you're all left with just newtons.
Thank you.
No problem. So that's a pretty simple, straightforward little calculation, but it also gives you an idea of the magnitudes of these forces. You could actually calculate the tidal forces, which is a little different thing. It turns out when you try to consider how much it pulls on one side versus the other, it turns out the tidal forces between the moon and the Earth is about twice as strong as the tidal forces between the sun and the Earth. So that's something you might learn about later if you decide to go into astrophysics or something cool like that, or astronomy. But that's a neat problem either way. So now let's go ahead and look back at sharing my screen and see the next problem I have written for you. I want you in this is number 4. I would like you to calculate a person's apparent weight at the equator and then at the North Pole, just assuming their mass is m. So this is a pretty neat little problem. What I'm going to do is I'm going to draw the Earth first, let you see what the issue is. So if I draw the Earth as a circle, we got to remember it's actually rotating this way. And of course, if you're standing on the equator on a little scale, like so, okay, Let me go ahead and stop sharing now that I'm drawing. So here's the Earth. The Earth is actually rotating like this, say, right? In order for me to rotate like that, I have to have a centripetal force pulling on me downward just to keep me from, launching straight out the page when I get to this point on the Earth. So I'll draw a free body diagram. And what I'll see is there is a force mg pointing this way, and then there is and I'll call that the positive direction, and then there's a force F scale pointing this way, and that's really what the scale will read. And of course the summation of the forces in the x direction, let me go ahead and draw an axis on that for the heck of it. Let's call this x and let's call this y. Okay, so the summation of forces in the x direction equals mass times acceleration in the x direction, gives me mg minus f scale is equal to m v squared over r. Okay, so I got to compute v and find out what r is. Well, r is essentially the radius of the Earth. So that's r Earth. And v is going to be 2 pi times r divided by the period. So basically we're saying it's going to rotate 360 degrees in 24 hours. That's technically not right. It's actually going to rotate 360.986 degrees per 24 hours because the sidereal day is actually shorter than a solar day. The Earth has to turn around 360 plus another 0.986 degrees, but this is close enough for what we're doing. So I'm going to say, when I'm plugging this in, I can say Fs is going to equal mg. If I pull this over to this side, the Fs becomes positive, and this will be minus mv squared over r. And this will become m times g times 1 minus v squared over gr. So now I can start working out what that is. That's the actual formula, by the way. You could call that an answer if you want, but I want to get it at least in terms of some number times mg so we can see what happens. So I'm going to put these numbers in. I'm going to say,
ask a question?
yes.
How did you factor out mg if there wasn't a g in the mv squared over r?
Yeah, that's one of those synthetic factoring out things that we do in physics a lot. So what I did was I imagined multiplying this by g over g, and then I just factor out that top g, because you can multiply anything by 1 and it's still the same value. So I put g up here and a g up here, and then I factored out this one and left that one down there. It's a neat little algebra trick that we do quite frequently. You get it?
Yes, thank you.
Okay, no problem. So this is actually going to be mg, which is what we normally expect, times 1, which would be exactly what we normally expect, but it's going to be minus. Now we put this up here, we're going to say 4 pi squared radius of the Earth squared over t squared times g times radius of the Earth. Okay, so we see that one of the radiuses of the Earth is going to cancel out. And what I can do now is I can say it's going to be mg times 1 minus 4 times pi squared times, now we take the radius of the Earth, which is 6.38 times 10 to the 6th meters, and we're going to divide that by 9.80 meters per second times, notice the one in the bottom canceled out, times 24 hours times 3,600 seconds per hour. And all that's got to be squared. I know I wrote that kind of small, so I'll rewrite it over here. Okay. So you see what's going to happen with the units here. I've got a meter up top and a meter on the bottom, so they're going to cancel each other out. I got a meter squared in the bottom of the bottom, but this is going to come out the meters, I mean a second squared in the bottom of the bottom, but this is going to come out to seconds, and then it's going to be squared, so it literally has no units in this, and this is exactly what we expect. So what I'm ultimately going to get is mg times 1 minus, I calculated 0.0337. Carrying one extra digit. So that's actually another answer as well. F scale is equal to this, but you could also say F scale is equal to, if we actually calculated that, that G, we'd see it's 9.76. So we'd say it's M times 9.766 meters per second per second. So you can see this is actually comparable, being at the equator is comparable to being at the top of Mount Everest in terms of your change in apparent weight. Remember, we got 9.77 for that. So now we're seeing, yeah, this is comparable at being at the equator. Whereas being at the North Pole, if we go back to the drawing up top, you got a scale right here, a person standing there, and they're just rotating. They're not revolving. So there's no centripetal acceleration they have to deal with. That free body diagram is F scale in the y direction and mg in the y direction downward. So you get Fs minus mg is equal to 0. So Fs is equal to mg. So that's the other part of the question. Any questions on that?
So acceleration is 0 for if you're on top of the North Pole.
Yeah, you have to do a little bit of acceleration if you get off the North Pole or the South Pole. As soon as you start to go down a little bit, you're actually revolving around the center of the Earth. Therefore, you have this centripetal acceleration that slightly decreases you, but it decreases your weight to a maximum of about 0.3% as you go from here to the equator.
So then why do we say acceleration was 0?
Mainly because the change is so small. So we can use 9.80 and we see we're never going to be off by more than about 1/3 of a percent, and 1/3 of a percent is pretty small. So we recognize that it's not exactly 9.8, but we realize that everything is pretty darn close. So unless we want precision more than 0.5%, then we don't need to worry about the addition of latitude and equatorial position and that sort of stuff.
Okay, and then what kind of acceleration do you have if you're on the equator? The centripetal acceleration?
Yes, it's the acceleration that keeps you stuck to the Earth, because when you're at that point right there, your velocity is straight out of the page. So something's got to be pulling you towards the center to keep you from coming straight out of the page. Well, that's your force of gravity. So part of that's going to be making the scale go up, but the other part's just making you accelerate inward. That acceleration inward part multiplied by your mass is the 0.033 that's being subtracted. Does that make sense to you?
Yes, I just have one more question.
Go for it.
How did you like distribute the G? Did you just put like 9.8 or?
How did I do what? How did I get big G?
No, so you know how you we went from mg just to m?
Okay, right.
How did you do that?
Okay, so if I take 1.01 and subtract from it 0.03374 and then multiply that by 9.8, I'll get that. So in other words, this is about 1 minus 0.03 is about 9.772.6, something like that. So if I multiply 0.97726 times 9.8, I should get this. Was I right on that, Miguel? I think you're typing it out on your calculator right now, aren't you?
Yeah, so I did 1 minus 0.0334
Yeah, you did 47 instead of 74. I'm always that way. Do-do-do. It's so
Did you
stressful.
distribute the 9.8 in?
Yeah, I just basically did the subtraction and then multiplied it by 9.8.
I got 0.96626. And
Okay.
then multiply that by 9.8. I got 9.469348.
Oh yeah, I was
Okay,
going with
too.
7736, but no, it was 6626. Good catch. Times 9.8, and you get, oh, yeah, see, I did. I think I might have made this error before. The answer should be, what did you say, 9.46?
Yeah, 9.469. So if you wanted to add like 2 decimal points, 0.47.
Well, that is actually a bigger difference than I thought.
So does that mean you would weigh less if you weighed yourself on the equator versus the North Pole?
Yes, your mass wouldn't change, but you certainly would weigh less.
Okay.
Isn't that because of the Earth's formation? Isn't it like skinnier at the equator and then like fatter at the?
It's actually the other way around. So I'm not even being correct by using the radius of the Earth like I did. I really should use the slightly bigger radius of the Earth. So that would actually make this factor a little smaller. Technically, the Earth is an oblate spheroid. So this radius is the biggest and this radius is the smallest. So yeah, I should correct for that. Actually, let's see. I think your book did this problem too, didn't they? Let me see what they got. Maybe my math was right somewhere else. They got a 0.0037 difference like I did. That's why I guess that's why I trusted it, because it looks like the same answer. G minus G. Yeah, I got the, yeah, see, they got the 0.0337 just like I did. I might have just made the mistake when I did this part down here. So any questions on that? All right, yeah, your book does something like this too. It's example 6.5 if y'all want to look at that. Maybe you might like their explanation better, I'm not sure. But let's try another problem now. I'm going to go back to sharing my screen. And here's the problem. So that was number 4. Now, number 6 is use the Earth's orbital information to determine the sun's mass. So earlier we actually worked out Kepler's third law, basically. You might not remember it, so I'll do it again. Basically, what you have is that the sun, if you just assume the sun's mass is huge, huge, huge compared to the mass of the Earth, and that is true. In fact, 99.99% of all the mass in our solar system is all in the sun. The other 0.001, or excuse me, yeah, 0.01% of the mass is in all the planets, the asteroids, the comets, and the Kuiper Belt objects, and Oort cloud objects, and all that good stuff. So it's really not that far off to assume this is like infinitely massive. And then way out here is the itty bitty Earth. This distance is, of course, 1.496 times 10 to the 11th meters. And what we do is we realize that the force of gravity, which is G times the mass of the sun times the mass of the earth, divided by the square of the distance between them, 1.496 times 10 to the 11th meters squared, that force right there has to be equal to the mass of the earth times v squared over r. Again, this is the same r as that one, okay? But the v in this case is 2 pi times this radius divided by 365.4 or 0.25 days, okay? But you got to convert that to seconds. So this is really what we're going for. So I'll start with that, gm star. Notice the, well, I'll go ahead and do it again. M sun over r squared is equal to m earth again, v squared over r. That's going to cancel out this r with one of those. Of course, v being equal to 2 pi, that r over period. We can see that this is going to become, and also let's go ahead and cancel out the mass of the earth like that. This is going to become g m of the sun over r times or equals 4 pi squared r squared over t squared, which gives us, let's say, g m over r cubed is equal to 4 pi squared
Could you
over
put
t
the
squared.
paper up a little bit, please?
Yeah, okay. Oh, yeah, see you. Gotcha. So this is a form, we normally solve it where r cubed is over here and t squared is over here and you have the constants, but I'm trying to solve for mass. So this is Kepler's third law, it's just in a weird form. I want to solve for the mass of the sun though, so I'm going to take this now and say that the mass of the sun has got to equal 4 pi squared r cubed over g times t squared. Did I miss anything? Everything looked like I did it right there. And this is actually how astronomers do this. When we find an exoplanet, that's helpful for us to determine the mass of the star that it's orbiting. But when we find the exoplanet has a moon, that's helpful for us to find the mass of the planet. And that's like, for instance, how we figured out the mass of Jupiter is luckily it had really 4 huge moons and they were all helpful, but it's actually got almost 100 moons to date now. So now I'm going to say the mass of the sun should be equal to 4 times pi squared times 1.496 times 10 to the 11th. And this will be, of course, meters. That's cubed over 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared times 365.25 days if I really wanted to, times 1 day is equal to 24 hours times 1 hour is equal to 3,600 seconds. Now I got to square all that junk. Okay. Let me let you see what I wrote. That's a 1.496. The pad's bouncing up and down. So when I go to take the pen tip off the paper comes up with it. So that's why it keeps crossing that, making my writing even worse than it is. Okay. So now we can actually calculate the mass of the sun that way. I've got 4 times pi squared times 1.496 e to the 11th. And now I'm going to cube that. And then I'm going to divide by, whoa, I got to get out of my exponent before I can do that. Now I'm going to divide by, and here I'm going to use some parentheses. I'm going to say 6.67 e to the negative 11th times, now I use another set of parentheses. I'm going to say 365 times 24 times 3600. We'll go outside of that second set of parentheses and put an exponent of 2. And the answer I get is 1.99257 9 times 10 to the 30th kilograms. So remember, we've been using 1.99, so that does work out consistently with that. And of course, I carried all these extra digits. I never used more than 3 sig figs in here, except for the 24 and the 3600. That's an infinite number. So I basically should have rounded this to 3 sig figs, which would be 1.99 times 10 to the 30th. Any questions on that? So I think that's pretty straightforward. Any questions?
Nope. Pretty straightforward, like you said.
No problem. Yeah, this stuff's pretty easy. The only thing that could make it hard is like if you have an assemblage of masses, say like at 3 at the vertices of an equilateral triangle, then you could say what's the force of gravitational attraction on this one due to this one and this one. Then you got to make vectors out of those forces and then add them as vectors. That's when it gets kind of at least time consuming. Not hard, just time consuming. So let's check the next scenario. That was number 5. I want to now calculate the altitude of a geosynchronous satellite. Okay, so geosynchronous means it rotates at the same rate that the Earth does. So you can put a satellite in orbit, let's say directly over Kansas City, Kansas. And if we did that, if it was in geosynchronous orbit, it would always stay directly over Kansas City, Kansas. And that's actually kind of relevant because that's the orbits that we put satellites in for DirecTV and Dish Network, and also the cable ones too, like we use for, cable companies aren't cable all over the world. They actually have a hub that gets satellite information at each of those little hubs, and then they send it out from their little hubs to your house via coaxial cable. So we're going to calculate a geosynchronous orbit. What we know is that, again, G times, in this case, the mass of the Earth times the little mass of the satellite is equal to the radius of the orbit squared. And that, of course, is equal to the mass of the satellite times v squared over the radius of the orbit. Okay. So I'm going to stop sharing the screen so we can see that now. This would be number 6. So that's what we have. That's the same equation we did before. But V is going to be 2 pi times the radius of the orbit over the period. And I'm going to actually go drill a little deeper and realize that the Earth goes through not 360 degrees, but 360.986. So if I really wanted to get a precise measurement, I should use not 2 pi r, but 2 pi r plus that extra pi over 180 times 0.986 if I really want to get it precise. But I'm going to leave it at this way. So now if I put this in, I will get again Kepler's Kepler's third law. Notice I'll have over R0 squared is equal to, I've already canceled out the M. Oh, I shouldn't have that V there. I was planning on getting rid of that sucker. So I'll have 4 pi squared R0 squared over T squared R0. So now you can see this R0 is going to cancel out one of those and we'll leave the rest. What I want to find is R0, but I really want the altitude. So what I need to do is take that altitude and subtract from it the radius of the, or excuse me, take that orbit and subtract from it the radius of the Earth. So let's just solve for the radius first. I'm going to say that r0 cubed. You can see if I pull these up here, that'll be r0 cubed. Then I just need to push everything else over there. So that should be g times the mass of the Earth times t squared divided by 4 pi squared. Okay. So r0 should be equal to the cube root of 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Trying to put the units in so y'all can see what's going on. The mass of the Earth, which is 5.98 times 10 to the 24th kilograms, times the period. Now, the period is the time required to rotate once around the Earth, which is revolving, but the Earth is rotating. That's why I use the words rotate and revolve. The Earth is rotating and the satellite's revolving, but that time is roughly 24 hours. So 24 hours is actually 23 hours, 56 minutes. That's the way I could actually account, or 54 minutes, because I could count for the sidereal day that way. But I want to say 24 hours times 1 hour per 3,600 seconds. And that quantity will be squared. And then all this will be divided by 4 pi squared. I think I got all my math right there. Notice this cube root goes all the way down, includes that thing in the denominator. So now I'm going to calculate all that. And then I got to remember to subtract the radius of the Earth from it. So I'll do 6.67 e negative 11 times 5.98 e to the 24 times parentheses 24. Whoa.
Are you cross multiplying those variables?
This is converting units, so I'm pretty much putting the 24 over the 1, and then the hour cancels out with the hour, and all I have is seconds left.
I'm talking about the formulas.
Like
Before you
here,
got those numbers.
yeah, that's one way I can basically multiply both sides by r0. That would make r0 cubed over here. Then I multiply both sides by t squared. That would get rid of t squared over here. And then I divide both sides by 4 pi squared, and then that would get that over there. So that's sort of what's happening.
By cross multiplying.
So 24 times 3,600, and now I'm going to square that. Whoa. Evidently, I'm going to just put a 2 next to it because I'm a crackhead. Okay, I got that. Now I'm going to say divided by parentheses 4 times pi and times pi again because I'm lazy. Okay, so this is going to be what's under the cube root. So I'll say this is equal to the cube root of, it looks like 75.421 times 10 to the 21. Notice the units here looks like they're just going to be meters squared to the square power, no, meters squared times the kilograms going to cancel out. That'll be newtons under kilograms, which is a meter per second squared. And then I'm going to multiply it by second squared. So I actually have meters cubed is the final unit under there, which is good because we've got to take a cube root of it. So now I'm going to say I'm just doing it old school because it's easier to do it. I just put the answer raised to the 0.333333 power. So that turns out to be 42.25 times 10 to the 6 meters. And remember, the radius of the Earth is 6.38 times 10 to the 6. So 6,380,000 meters. And I want to subtract that from 42 million meters. So I got 42 million. I might as well round. Oh, I'll keep this as 250,000, even though these are all doubtful digits, of course. Actually, that one's not. The 5 is, though. So now I subtract those two, obviously 0 minus 0, 0, 0, 0. I have to borrow from this number over here to make 15. 15 minus 8, of course, is 7. This is now 1. I got to borrow from that. That becomes 11. 11 minus 3 is 8. And this is now 1. I got to borrow from this one over here. So this is now 11. 11 minus 6 is 5. And that's 3. So, in fact, the orbital altitude is actually 35,870,000 meters. So the altitude for a geosynchronous orbit is equal to 35.9 times 10 to the 6 meters. Any questions on that? I even did old school arithmetic with my borrowing and everything. I felt like a champion.
How you get rid of that small m?
What's that now?
Like at the beginning when you had GMO times m.
Right. There are m's on both sides. So if I multiply by 1 over m on both sides, this one will disappear and that one will disappear. A lot of physics is about solving equations symbolically rather than putting in numbers. So y'all might want to even practice a little bit of that. There's some refresher math stuff in the appendices of your textbook, so you can check that out. Or you can check out some of the stuff on my YouTube channel. I've got problems where I work stuff like this, but you know, this is going to go up on the YouTube channel, so you'll be able to make that out there as well. Anybody have any questions, or anybody verify my calculations and make sure I didn't completely screw it up? Oh, actually, yep, that looks pretty good. Good deal. You can, if you want to, you can also use that. Go back now that you know the altitude and calculate the actual velocity, see what that is. All that's kind of neat stuff to know. And you'll see that it is actually quite fast. Imagine, you know, the Earth moves about 15 degrees per hour. You know, it rotates 15 degrees per hour roughly. And at 15 degrees, that's a big swath of Earth. But now imagine that that's extended another 35 million meters up, or 36 million meters up. Imagine how fast that's going by. We're talking, you know, on the order of hundreds of meters per second at the surface of the Earth. But now you're going to say, like, you're water skiing behind a boat that's turning and you're slinging out to a larger radius. So you're going to go even faster. So I think that's about it. We started at 11. We're supposed to go to 12:15. Does anybody have any other questions? I think I've covered just about everything. You can learn some of the details about orbits and stuff if you'd like. Go ahead.
So the test is due tonight at 11:59.
Is that what I posted?
I think that's what you said before.
Let me check, because I don't like to just say that off my memory. So I'm gonna look real quick and see what I set up. So I'm gonna go down here. I'm gonna go to my modules, and this is test 2, right?
Yeah.
Okay. Yeah, I think that might be right. Let me see. I'm checking. My computer doesn't like where I put everything, so it keeps scrolling me back. February 24th. That was last night at 11:59.
I thought you'd said you'd make it tonight because our homework was due last night.
That's right. I tell you what, I'm going to do you better. I'm going to push it back to let's push it back to, there's the part I was looking for. It took my screen away. I'm going to give you till the 27th at 11:59 p.m.
That works perfectly for me.
Okay. Yeah, I remember now as you said that. Sorry, I hope that messed anybody else up.
Getting a small heart attack. I was like, oh
yeah.
no.
When I looked at it and saw the 24th, I'd be like, oh yeah, he's going to love this answer. So yeah, if you want to look more details in the book, it's got cool things like Lagrange points. Those are interesting things. You know, you can imagine a point between the Earth and the Sun where the gravitation from the Sun is able to cancel out the gravitation from the Earth, and that would be one of the Lagrange points. And there's all sorts of cool Lagrange points where there's basically like no force of gravity left there. By the way, that is not what the satellites and what the space shuttles and spacecraft do when we send people to space. They are in what they call microgravity, not because of zero gravity, but because they're in free fall. So that's another big physics concept you should definitely learn from this chapter. I don't go as deep on this. I mean, I would like to, because that's the stuff that I like to play with, talking about the principle of equivalence and curvature of space. But I really just try to blow through this chapter rather quickly. I will tell you that Einstein comes along in 1905. He had a banner year. He publishes a paper on the photoelectric effect that is so successful. He knows, and his wife knows, she also happens to be a physicist, are so confident that he's going to win the Nobel Prize for it, that the terms for their divorce were that Einstein didn't have to pay her anything, but when he won the Nobel Prize, he would give her the money. So he did that. He did Brownian motion paper, which could have won him a Nobel Prize. That was the final proof of the existence of atoms. And he did special relativity, which no one even saw there was a problem of electrodynamics. He not only saw there was a problem, but solved it. And then a day later, he sent in as an appendix E equals mc squared, which explained why how the sun worked and how we could make nuclear weapons. Both of those could have won him the Nobel Prize, except for the nuclear weapons part. They usually try to go cheap because Nobel was feeling bad about gunpowder. So anyways, that was 1905. And he spent the next 10 years basically trying to figure out the part that included gravity. So basically, he literally said, well, we call this special relativity because it's in the special case where it looks like Galileo's law of inertia applies. That does not include gravity, because if you just looked at a photo or a film of the planets orbiting the sun, you don't see any forces pulling on the planets, yet they're not going in straight lines. So that's a non-inertial reference frame, because in an inertial reference frame, the planets would go in straight lines. You have to imagine some imaginary force, gravity, for it not to be doing that. So he considered that a non-inertial frame, and he went and spent the next 10 years of his life learning the mathematics required for him to make sense of the world in light of special relativity. What he came out with was the general theory of relativity, which he published in 1915, and it wasn't confirmed, I think, until 1916, when Arthur Eddington, the British astronomer royal, confirmed what Einstein predicted, which is light coming by our sun would be deviated by a very specific number of degrees as a result of the gravity of the Earth, of the sun on that light. And he instantly became famous. Now, what his ultimate conclusion was is that there's no way you can tell the difference between accelerating upward and a force of gravity, at least on a small scale. So if you had a perfectly soundproof elevator shaft that in one case you attached to a rocket that was accelerating straight upward at 9.8 meters per second, if you did an experiment like drop a penny, you would determine that it's falling down at a rate of 9.8 meters per second, and you would say, oh, I'm sure that's just gravity. But if it was sitting on the surface of the Earth, it'd be doing exactly the same thing. So that principle says you can't tell the difference between gravity and acceleration. Now, if you made that elevator big, like say the diameter of the Earth wide, and you drop a penny from the far right side, that penny would fall down into the right, or excuse me, down into the left. If you dropped it from here, it would fall down this way because it's going towards the center of the Earth. So over a big scale, you can tell the difference between gravity and acceleration, but on a small scale, you can't. And then he used that to say, well, the laws of physics should be the same for all observers. And that specifically means that the laws should be cast in tensorial notation, because it turns out in tensors are what allow you to convert from one coordinate system to another with this multiplication by a matrix, basically. And if you want to make your F equals ma an equation that holds up in all coordinate systems, no matter how jacked up they are, you'd write them in tensor equations. So he had to go back and learn tensor calculus, and he had to go back and learn differential geometry. And ultimately what he came up with was the general theory of relativity, that in the realm where we had been using Newton's laws of physics, it actually reduces to the actual equation GMM over R squared. So it does, but it's got a little correction to it so we can see where the error is. But that's part of what Bohr called the correspondence principle when he was making quantum mechanics. He said we shouldn't introduce a new theory that's going to help us with, you know, matter at the very small scale unless it gives us the same answer in the very large scale that we already know. Otherwise, you're just doing like ad hoc solutions. So it fit that correspondence principle. It also predicted basically that space is four-dimensional. It's left, right, that's one dimension. Perpendicular to that is up, down, that's another dimension. In, out is perpendicular to both of those, that's the third dimension. And then perpendicular to those three, oddly enough, is a fourth dimension, and that's our time dimension. And in that four-dimensional space-time, mass tells space how to bend, and then space tells matter how to move. So you picture our solar system like a trampoline with a really heavy bowling ball in the middle. And that really heavy bowling ball makes a pucker like this of the trampoline. Now, if you shoot a BB, not towards the center, but towards the edge or a little bit out from the edge, then that BB will roll along that incline and then start circling around until friction wears it down so much that it spirals into the center. But without that friction, it's going to go that direction always. And it's not a force, quote unquote, pulling it between the bowling ball and the actual BB or marble. It's actually the force of space or the shape of space that's causing the marble to go into an elliptical orbit. And that's ultimately how he explained gravity. Gravity is not a force. It is a mass causing a pucker in space. And that pucker in space causes space to not be flat. And when the universe is not flat, that means the normal laws of geometry, like the shortest point between two lines, between two places is a straight line. That's not valid. The sum of the angles inside of a triangle is 180. Not valid. Two parallel lines never meet. Not valid. Two perpendicular lines never meet. Not valid. All those things are different when you talk about curved space. And when he did that, he also was able to predict gravitational radiation, which is gravity waves. And just in September 2015, we confirmed that. Literally 100 years after his theory was published, we actually were able to predict with his theory what we would see if two black holes collided in terms of gravitational radiation or gravity waves. So it showed the existence of gravity waves, which had been hypothesized by Einstein. And not only that, it showed us again that Einstein's equations were right on the money because it worked perfectly. And it was the first exact one-to-one confirmation of the existence of a black hole, whatever that may be. We don't necessarily know, like when you go inside of a black hole, is it really a tear in space-time? We can't answer that, and we might not ever be able to answer that. But we do know it at least acts like something that's consistent with a tear in space-time because it gets, very, very tight. That cone of the trampoline gets very, very small if you picture that as a black hole. So we got a lot of cool things coming out of Einstein's general theory of relativity, even 100 years later. And it's amazing that he, in his brain, using Gedanken's thought experiments, was able to come up with the general and special theories of relativity. So that's about all we're going to do about relativity. You might want to read about it for the fun of it. That's what we're going to do in the general relativity, I should say. General relativity is a little complicated for you to do the math part of it. But I will tell you one thing: when we learn conservation of energy, the equation for the Schwarzschild radius of a black hole is exactly equivalent to the radius that you get when you assume that it takes the speed of light, an object to go the speed of light before it can escape the gravity of a planet. and you calculate that radius, sure enough, that radius gives you the same radius that we get from Einstein's general theory of relativity. So when we do that, I'll point that out. Any questions on any of that?
Yeah, I do. This is Alexi or Richard, but yeah. So I was gonna ask, what kind of job, Professor Younger,
Yes.
relevant to like what you were just talking about? Like, I know it's physics, but like what Einstein was doing, like, how did he like make money? Like, because if he was
He was a professor, he would have won. Of course, he did win the Nobel Prize. He was the world's leading scientist, so a lot of universities competed for him. I'll give you some perspective on that. My PhD advisor was braggadociously telling us he was the highest paid non-medical faculty member at Chapel Hill. And when he got fairly famous, Cornell picked him up, and from what had been suggested to me, he might have made 4 or 5 times as much money at Cornell as he did at Chapel Hill. And public records showed that Chapel Hill faculty members were making on the order of 160 grand a year. So
yeah, is Cornell in Massachusetts or Pennsylvania?
Cornell's in New York.
New York. Okay.
Yeah, Ithaca, New York. It's where Carl Sagan was. Richard Feynman was there for a little while. Hans Bethe was there for a while. Well, Hans Bethe, I think, retired from there. So yeah, it's a really well-respected university, especially for
you know what, like the most famous alumni is from a university?
He's probably the most famous over history, but probably right now it might be Ed Witten. He's got the Lucasian Professor of Mathematics at Cambridge, which is a position that Newton held. He's the guy that invented, one of the guys that invented string theory. Green, Shorts, and Witten did that.
Yeah, but how about like someone not like as like academic as that? Because like, like someone who's more like published in the media, like Elon Musk, for example.
Brian Greene or Nicola, what's his name? Michio Kaku. I can't remember his first name. Michio Kaku. He's written a good quantum field theory book. He's also written some popular books. He's been on a lot of movies. Neil deGrasse Tyson's another one, even though he's not at an academic institution. Phil Plait, he's no longer at an academic institution either, but he's pretty famous. Does a lot of work for movies. Kip Thorne, who just won the Nobel Prize, he made the movie with Matthew McConaughey. Was that the one called Gravity?
I know, I saw Gravity.
Yeah, not only did he assist greatly in that movie, he bragged that he got like 3 publications out of making the movie because he was able to do some cool calculations to make sure things worked out properly for the movie.
Yeah, like a funny thing is like when I look at like colleges,
everybody is free to go, by the way. Sorry about that. Go ahead, Alexi.
If colleges in California, like if I went there, like I look at alumni and like all of them are like actors.
Yeah, that's kind of a sad thing. And not completely sad. I mean, some actors are really brilliant. Like Chris Christopherson. He was a Rhodes Scholar. Then he became, from a Rhodes Scholar, he became the night janitor at a recording studio. Come to find out, he was really brilliant and could sing quite well. So he's one of the smartest people we've ever had in acting. A lot of people think Ronald Reagan was really smart. I don't agree with that quite as much, but I do know he was, one of our better presidents, or got one of the better results from presidents. So sometimes actors can be really good, but yeah, I would rather academics be the quote unquote Illuminati, or the or at least the people that everybody aspire to be. I would much rather that be an academic person. But now it's even, medical doctors are more respected than professors, which is kind of a shame, but professors still do okay. Right?
It's weird how like
get medical school.
All the media goes on to like sports and like entertainment instead of like the real good stuff like physics or something.
Yeah, and you also don't want to be too elitist. I mean, the reason why sports players, athletes, like poor Tiger Woods, get so much money is one, they work their butts off and get a lot of get some serious skills. I mean, they're not just born awesome. They really worked on it, and maybe they had some natural ability as well. But at the end of the day, you can write down everything that he went to and see how many people came, and compare that to the events that he didn't go to and see how few people came, and you can point to a dollar amount that he's worth. That's the problem with professors. It's harder to point to what professors or academicians are worth. The same thing even with elementary and middle school teachers. How do you point at what that's worth? It's real easy to figure out what a professional athlete's worth, because when you don't have good professional athletes, you get low turnout into your football games, and the football game revenue can be, you know, hundreds of millions of dollars per year. So they are entitled to a fraction of that. We as teachers, and you know, they should be entitled to some fraction of the wealth of the people that leave them as well. But it's really hard to do a calculation for that.
So like, you know, another interesting thing is like I heard that like, so if we look at like academics versus like athletics, so that's kind of I see the world in two halves. Like it's either like the athletics or like entertainment and like all the other stuff besides academics. And then we have like pure academics, which I think like pure academics is, I think, math, right? Is that like the purest form?
Well, math, there's also experimentalists, there's you know, bioengineering, those sort of things. These people are academics and they do research, and some of them go on to prestigious positions at and private sector companies, and that's good too, so they can make you know, good money. But you know, a lot of research is done at the university, so they, you know, a lot of people say the German model of education is the right one, and that is the purpose of the university is not to teach people, but rather to create new knowledge.
Like, don't you think the reason why the entertainment business or like athletics make more money than the academic business, because that side of the, like, that side of, I don't know, like whatever, it's like controlling the academic system, like it's dominating, it's like influencing. Like we already have, like, for example, like sports in college, whereas like if we just were like an academic society in general, we wouldn't even care about like giving scholarships, like full rides to like great sports players.
Yeah, I mean, part of that helps. So I don't want to downplay the importance of athletes and athletics. Chapel Hill, where I went and did worked on my attempted PhD, is pretty well respected for many sports. It's led the nation for decades with the world's greatest women's soccer team. The basketball team has been amazing too. Football off and on is good. Women's field hockey is amazing. Men's soccer is not bad. Lacrosse is not bad. That sort of stuff. So it's been really good. So the flip or the positive side of why that's good to, you know, celebrate athletes is they bring in a lot of money for the university, and then the university can use that to pay high salaries, like to my old PhD advisor, so that he can get grants to do research. And you know, he was on several multi-million-dollar grants, and that, you know, I got paid out of them to do my research. So it does help. So yeah, I see that it's definitely valuable. I just think, like I said, I don't, either people don't want to do the calculation, people don't want to admit to the calculation, or what, but it's a lot harder some way of knowing exactly how many dollars a teacher's worth. Does anybody else have any other questions while we're just shooting a breeze here? I see some people are sticking around. Go ahead and ask a question if you have. I know you might have another homework problem, Lauren. Duncan,
Yeah.
Heather, Rowan. Okay. Well, yeah. So that, yeah, that's an ongoing thing, and I don't mind it. You know, I love college athletics. I used to love watching football and love watching tennis. I tried out for the tennis team in East Carolina. That was fun and humbling. And East Carolina does not, at least then, did not have a good tennis team, and I was still very humbled, despite the fact that I could play quite
Like,
regularly.
what's the connection of like how does like athletics and like academics like specifically act together in like a symbiotic relationship? Like I don't see like how athletics benefits academics, but I do see how like academics benefits athletics.
Yeah, money is the deal. I mean, money makes things happen. So if athletics can bring money into the college, that money's not necessarily beholden to stay in the academic or in the athletic portion of the college. It can go to the academic portion, and in fact, it does. A lot of it does. So you
Well,
know,
how does
Notre Dame.
athletics bring money to the college? Because I heard like you spend money for college athletics. Like the money has to come from
That
somewhere.
used to be the case, that you spent more for, you know, at one time, like in the late 80s, it was found that like only two football teams in the nation made more money than they spent. And that was like Notre Dame and Florida State or something.
But how do
But
they make
since
money
then,
by
we've got so many
athletics?
bowls. They make way more money than they spend now.
How do they make money in college athletics? I don't understand. Like, where do they get the money? Like when they
Charging for attendance, which is never tennis, by the way. I mean, Stanford. If you're at Stanford, you can charge to get people to come watch tennis because that's where John McEnroe went and various other really good pros. And they are them and some other elite universities are really good at that. They can charge softball fields and with the really good teams like had Judy Finch and all those people. Those can actually attract money, so they can get money that way. But like I was at Chapel Hill and my then wife worked their recreation facility, and Nike sponsored the university, so we got free track clothes, free shoes, free glasses, and stuff like that. Nike was literally paying Chapel Hill just to be their brand. So when UNC goes on the
sponsored,
field, they're wearing all Nike.
So like I don't see any hardcore academics going around, but I do see a lot of hardcore athletics where people are screaming in the stadiums. I don't see that in the academic world.
Nah, and it's sad. I mean, Richard Feynman talked about that a little bit, and surely you must be joking, Mr. Feynman. Someone asked him why he thought there were so many Jews. Specifically, they were talking about Jews. Why there were so many Jews in esteemed academic positions, and he remembered an incident where his mother and him were at home, and they had two visitors, and one was a medical doctor and one was a teacher, and she was just really excited. She said, "Oh, what fame do I owe? What do I owe all this fame that I've had now a teacher and a medical doctor come to my home to visit?" So,
So like I
respect
want
for
to give you like a
education.
real life example of what I mean, like how like no one cares about academics, like in the deepest sense, because I know a guy that his name is Brandon Nakashima. He's 19 years old. And I actually played him in some tennis tournaments and I beat him once, but he's ranked 133 ATP in the world.
Wow,
and so he's
that's good.
rising.
So the force will also be the same for the X direction too. Well, I'm talking about like setting up the formula for it.
Yeah, you always just find all the forces acting in the X direction, and the ones that are pointing in what you call the positive X direction should be positive, and the ones that are pointing in the negative, what you call the negative X direction, should be negative, and then you set that equal to m times a. This one, we knew it had to be accelerating because they told us in the problem is accelerating. And then just drawing the diagram, you knew it had to be accelerating in the X direction too, because there wasn't anything counteracting this force. So we had to leave it as ma instead of m times 0. And the reason why we had to leave it as ma is because they're, according to Newton's first law, an object in motion tends to stay in that state of motion unless acted upon by a net external force. This clearly has a net external force, so it must be not maintaining that motion.
Is that negative 7.5?
Yeah, there was a negative in front of this, but that's what I was telling you. I chose a coordinate system in which this way was positive, this way was negative. Someone might have chose the other way and got positive. They're really just asking for the magnitude of the acceleration. So 7.507 is right.
So I could have said, if I want to find like the X part, I could have just said mg cosine plus ma, and wait a minute. I was just trying to like put it into terms. So I could have just said, oh man, no, hold on. I had it mixed up.
Yeah, you don't want to mess around with moving the